Okay, so you should have cat 2.3 in front of you. And so if we just get started, so the first question should be fairly straightforward. So potassium chloride, obviously ionic. Lead and mercury are both metals, so the answer is B. Which one of the following is composed of small molecules? That'll be the one that's covalently bonded. So graphite, although it's covalently bonded, is a giant structure, shown down here. That's obviously not a molecule. Sodium chloride, again, ionic. Diamond, giant covalent, so it has to be water. 3. Complete the following sentences by adding the missing words. Fullerenes are forms of carbon in which the atoms are arranged into tubes, which would look like this. Or the other kind of fullerene you can get is this kind of thing, known as a buckyball. So the answer for this one would be balls, or spheres would be okay as well. One possible use of fullerenes is to deliver, not blood, unfortunately, but drugs. So how that works is you can put the drug can be put inside this as a kind of cage, which can then be transported into a particular location in the body. Okay, so on to the next question about graphite. If we look up here, we've got graphite is made of carbon atoms. What is unusual about the bonding of carbon in graphite? Bonds to 3. So it should be bonds to 3 other carbon atoms. Bonds to 3 other carbon atoms. Unfortunately, this person has not been clear enough when they've said bonds to 3 what, so we can't give them the mark for that. Also, they've written here forms a delocalized electron. I'm not sure forms would be the correct word to use there. They're right that there is a delocalized electron for each carbon atom, but that's not related to the bonding. The bonding is that it's only 3 when you would expect carbon normally to form 4 bonds. What general name is given to this kind of structure? Giant covalent. That's correct. Graphite is very soft and a good conductor of electricity. In terms of its structure, explain why graphite is very soft. Weak intermolecular forces between its layers. Correct. I can give that 1 mark. And obviously, whenever we talk about the forces between particles, you then need to relate that to how easy it is to overcome those. Okay, so the reason that graphite is soft is that those intermolecular forces can be easily overcome. So you would say weak intermolecular forces between its layers, which can be easily overcome. Okay, moving on. This question is about changes of states of substances. Explain how a rise in temperature can cause solids to melt. Let's have a look at this answer. Heat causes increase in kinetic energy of particles. Good. They vibrate until they lose their fixed structure and become free to move. Excellent. Yeah, that's a fantastic answer. All right, so if you've written something similar to that, give yourself 2 marks. Explain why less energy is required to melt a solid than to boil the liquid formed. The particles are not as compressed, they can move around each other. It's kind of on, there's a bit of thinking going on there. It's kind of right, but I'm not sure how much it's really answering that question. So I'm not going to give that mark. If we look at a diagram of what's actually happening, you can see that when we go from solid to liquid, obviously we have this fixed shape here, and then there's no longer a fixed shape here. But in terms of the distance between each particle hasn't actually changed. And you should remember that. Hopefully you did an experiment earlier when you were at school where you tried to compress a solid in a syringe and you tried to compress a liquid in a syringe, and you found that neither of them could be compressed. And that's because there's actually no difference between the distance between the particles. However, when we then go to a gas, the particles now are much further apart. And that's why it takes much more energy generally to do this transition, because here we break the force between the particles, but they don't move that far apart from each other, whereas here we're really, separating them to a larger distance. So for this answer here, you would need to write something about the distance between the particles is increased significantly. Okay, let's go on. Yep, this is correct. So it's a gas because it's above its boiling point. It's a liquid because it's between its melting point and its boiling point. Very good. In terms of intermolecular forces, suggest why propanal has a higher boiling point than ammonia. Requires lots of energy to overcome strong intermolecular forces. Would I give this the mark? It's correct. The problem is that it's asking you to make a comparison by saying one is the propanal is higher than ammonia, and the way that this is worded, it isn't done in terms of a comparison. So really, instead of saying it requires lots of energy to overcome strong intermolecular forces, it would be better instead if you'd said requires more energy to overcome the strong intermolecular forces. It's quite a subtle difference, but it's important. Okay. All right. Let's go on. So, when comparing the melting points and boiling points of substances, in what graphical form should the data be presented in? Okay. So, if we think about making a graph. Okay. So we got substance 1, substance 2, substance 3. And up here is going to be temperature of your boiling point or your melting point. Hopefully you can see that because these three things are unrelated to each other, they're not on a continuous scale. This could be water, methane, and ammonia. It's not a continuous scale of items. Then really, you should be looking at a bar chart. Okay. When I did get a chance to mark some of these before we finished school, a lot of people in here wrote table, that the data should be presented in a table, which I don't really understand why people have chosen that, because it states quite clearly in the question that it should be in graphical form. Okay, moving on. Substances can have different types of bonding and structure. Complete the table below by inserting the missing words. Iron is metallic, sand is covalent, and water is molecular. Excellent. So the only one there that you might not have been familiar with is sand, which is silicon dioxide. Don't get confused and think that this is a molecule. It's not a molecule, it's a giant structure, so it looks quite similar to diamond. Okay, so this question's about cycloalkanes. Alright, so we didn't get a chance to cover this in lesson, but this cycloalkanes are just chains of carbon and hydrogen which are in a ring. So the property is able to form rings. And then in the box above, draw the structure of the third member, so that will be 5. So this person has done a good job here. That's 1, 2, 3, 4, 5 carbon atoms. Excellent. Okay, so they've chosen not to show the carbon atoms, which is fine. If you did show the carbon atoms, it would just look like this. And then you would have, on each one, you would have your 2 hydrogens. Like so. And then it should be fairly easy to deduce the general formula, because each carbon atom has got 2 hydrogen atoms attached to it, so it's C2H-N, so that's correct. And then if we carry on, suggest what these figures tell us about the relative strengths of the intermolecular forces as the number of carbon atoms increase. As carbon atoms increases, intermolecular forces become stronger. Yep, excellent, because as we go from 3 carbon atoms to 4 carbon atoms to 5 carbon atoms, the boiling points are increasing, which means the intermolecular forces are also increasing. Okay. This is the structure of diamond. Each one of these lines here, these are all covalent bonds. That's correct. Explain why a diamond has a high melting point, because it requires lots of energy to break covalent bonds. Correct, but you need to state, so I'll give you 1 mark for that, but you need to state that when diamond melts, 4 covalent bonds are broken. Just to make it 100% clear what's actually happening. Alright, and if we go to the last one, explain the difference in the physical properties of these two substances. So we're comparing here chlorine versus sodium chloride. Alright, so really what you should be doing here is you should be saying that this is a molecule or molecular, this is ionic, okay, and because it's molecular it's got weak intermolecular forces, and weak intermolecular forces don't require much energy to overcome. And ionic, we've got strong electrostatic attraction between ions, which do require a lot of energy to overcome. And getting all that information down would get you the 6 marks. So let's have a look at what this person has written. Chlorine gas, Cl2, is a covalent bond between 2 chlorine atoms. I think perhaps just a slip of the pen there, what they meant was has a covalent bond between 2 chlorine atoms. It has a weak force of attraction between what? Okay, are you talking about the attraction between the 2 chlorine atoms, which is very strong, although not electrostatic, or are you talking about the attraction between 2 chlorine molecules, which is weak, but again is not electrostatic? So they haven't been specific enough here. Hence requires little energy to break them. So maybe I can give them the benefit of the doubt and assume that they meant between molecules there. So that would be a correct statement. Whereas sodium chloride is formed through ionic bonding, metal and non-metal, correct. The transfer of electrons forms a strong electrostatic attraction. Now actually it's not the transfer of electrons that forms a strong electrostatic attraction. There is a transfer of electrons. So you have a sodium atom and a chlorine atom. You transfer an electron from one to the other, which gives you Na plus and Cl minus. And now there is a strong electrostatic attraction because they are oppositely charged ions. Okay, so I don't like this wording. It's not the transfer of electrons that forms the strong electrostatic attraction, it's the oppositely charged ions which causes the strong electrostatic attraction. But it does require a lot of energy to overcome. Alright, so on the right lines, but could do with a little bit of work.